All right, okay, guys, so let's start. Okay, so today, we first kind of finish the last question from the discussion yesterday. Okay, and then second kind of we continue the chapter 17. Okay, hopefully we can finish chapter 17 today. Okay, but if we cannot finish, okay, so we will a little bit left over leave on kind of Monday. Okay. And on Monday we'll vote to which day we'll do kind of the quiz. That should be quiz 4 now. Okay, so maybe Wednesday or maybe on Friday. Okay, so even on the Thursday. Okay, so if you have any question again, you can type in the chart window. Okay. All right. Okay. So for chapter 17, actually kind of a lot of tricky thing about kind of synthesis design. Okay. And especially you try to put multiple functional group onto the benzene ring. Okay, so like this one. Okay. So first you need to consider kind of the directing effect. Okay, relative positions. Okay, so for this the two substitute group. Okay, so for here. Okay, so you see kind of these two substitute groups kind of the meta. Okay, so meta disubstitute. Okay. So that means kind of you have to introduce kind of meta director first, okay, and then do the substitution ES next and ES, okay. That's can give kind of the meta disubstitute kind of the benzene, okay. All right, so then you find kind of this is kind of the ketone is the meta director, but chlorine is kind of also para directors, okay. So that means kind of we need to introduce kind of the this ketone, okay, so the acetate group first, okay, and then do the chlorination, okay. Right, so now we do the kind of the Friedcraft the acylation first, okay, introduce this one, okay. All right, CR, okay, and then aluminum chloride, okay, so that's the can add the kind of acetate group, okay, onto benzene. All right. And then second step, okay, so we do kind of the chlorination, okay. Yeah, that's can directly put kind of chlorine on kind of meta positions, okay. So if you do the chlorination first, okay, and then do the FC acylation, okay, it's two problem, okay. Once kind of the you put kind of the first kind of if there's a deacting group, okay, so that's the deacting group, okay, so chloride, okay. On the benzene, you cannot do any Friedcraft acylation, okay. Second, kind of even you can do it, okay, so we won't go kind of a meta position, we go kind of also para positions, okay. Yeah, so that's something keep in mind, okay. So in end of this chapter, okay, so I'll talk about the more synthesis design, okay, and then we have practice more questions, okay. All right. All right, so now we continue the chapter 17, okay. All right, so on Wednesday, okay, we learned the one nucleophilic substitution reaction. That's here the diazonium reaction, okay. So so this one, okay, so we convert kind of the aniline, okay. So keep in mind, okay, it has to be kind of the aniline, okay. So you cannot use the other. Any kind of aromatic compound, okay, has to be kind of NH2, okay. Right, and then do kind of two-step reactions, okay. The first step, okay, so we use sodium the nitrite, okay, so NO2, okay. And then under acid condition, okay, you convert it to kind of a diazonium kind of the cation, right? And then second step, okay, you do kind of nucleophilic substitution reactions, okay, nucleophile coming, okay, replace kind of N2. Yeah, so that's we learned on the Wednesday, okay, and so pretty useful reaction kind of you can convert to kind of OH kind of nucleophile OH, iodide and fluoride and those CN, okay, so those you cannot prepared by ENS reactions, okay, ENS reaction, okay. But only problem for these reactions kind of why it's kind of not so popular as kind of ENS reaction. First, because you have to start with kind of aniline, okay. Second, okay, so the intermediate, that's diazonium, okay. So it's kind of explosive, okay. So kind of not so stable, okay. So sometimes the accident happened, okay. So that's why, okay. All right, and then second, okay. Second kind of here the nucleophilic substitution reactions kind of addition elimination reaction. Okay. So for this reaction, okay, so there are kind of here the two requirements for the starting material. Okay, so it's right two. Okay, the first, okay, so you have to make sure that the start with here some kind of halogen, okay, on the benzene ring. Okay, so yeah. Yeah, so that's kind of a lean group. Okay. And then second is kind of the there's the electron withdrawing group, okay, on also para positions, okay. Yeah, also all para, doesn't matter which one, okay. So that's make this reaction kind of actually kind of least useful kind of aromatic reactions, okay. So because a lot of limitation for the starting material, okay. So pretty much the reaction happened like this, okay. So you have kind of the halogen first, okay, and then there's kind of the electron withdrawing group, okay. So I only draw kind of on the para positions, okay, can be also on the also positions, okay. All right, and then you apply some kind of nucleophile, okay. So yeah. All right, so that's nucleophile will replace kind of this halogen, okay. Yeah, so that's finish the whole reactions, okay. And so for the mechanism of this reaction, actually kind of not required, okay, but I can draw you, okay. So that's why we call kind of the addition elimination, okay. All right, so. Okay. Addition elimination, okay, so you add kind of your nucleophile first, okay. Right, nucleophile normally can make charge, okay. So you add onto kind of pretty much the same position as the halogens, okay. Right, and then you open the cis theta bond, okay. So that's actually kind of not so common, okay, because the electron rich environment for the benzene, okay. But if you have really kind of the negative charge kind of species, you can do this way, okay. So that's less common, okay. And also that's why we have kind of electron withdrawing group in the benzene case. So that's help kind of help kind of decrease the electron density on the benzene case and make it kind of relatively a little bit stable case. So right, something like this. Okay, so negative charge kind of lone pair electrons on the benzene case, and then that's the addition. Okay, and then once this lone pair electron shift back, okay, kick off the halogens, okay. And then give you kind of the substitution kind of the product, okay. And one example is showed here, okay. So we have kind of the 2,4-dichloro, 2,4-dinitro, okay, chlorobenzene, okay, and react with kind of the amine, okay. Amine is kind of very good nucleophile, okay, can replace kind of as a nucleophile attack kind of the cis theta bond, okay, and then also replace kind of the CR, okay. Okay. And for this reaction, okay, so K things here, okay, so this guy, okay, K intermediate, okay. And why is kind of electron withdrawing group, okay, because the electron withdrawing group kind of stabilize the intermediate, okay. Stabilize the intermediate, okay. So that's kind of move the reaction forward, okay. And another tricky thing about this reaction is kind of it depends on what kind of the halide, okay. So they have kind of different reaction rate, okay. So fluorine kind of has the highest kind of reaction rate, followed by chlorine, and then followed by bromine, followed by iodide, okay. So that's kind of quite interesting, okay, because we will learn kind of the SN1, SN2 reactions, okay. So they have kind of quite opposite orders, okay. So iodide kind of best link group followed by chlorine and followed by kind of bromine, followed by chlorine, and then followed by kind of the fluorine, okay. But here totally opposite, okay. reason for that kind of still this intermediate, okay. So if you have kind of so if we electron range go kind of better electronegativity, okay. We do this, okay. Higher electron negativity, okay. Higher electron negativity, okay, and then this intermediate kind of more stable, okay, because that's hard to hold electron, okay, like this way. Hold electron decrease kind of electron density, okay, so because this not kind of too much electron on this bending, okay. Hold it, okay, decreasing electron density, and then make it kind of more stable, and then more stable kind of lower energy barrier, and then higher electron E there, okay, so stabilize the intermediate, okay. So stabilize the intermediate, okay. So that's why kind of the leaving group here in this kind of order, okay. All right, and then give you guys kind of another final example, okay, for this the addition elimination, okay. You see here addition elimination, okay. So this reaction actually kind of the pretty last common, okay, because too much requirement, okay, for the starting material, okay. You have kind of reaction group has kind of hydrogen has be kind of also paired positions, okay. Why is auto pair? Because the only auto pair kind of delocalize kind of negative charge into kind of electron visual group, okay. All right, so we have this nucleophile, okay, and then react with this substrate, okay, and then we can get kind of this one replace the fluorine, okay. So that's one example, okay. Okay, so now we move to the third nucleophilic substitution reaction, okay. This time kind of elimination followed by addition, okay. So very interesting, okay. So we just learned kind of addition followed by elimination, okay. So that's the one kind of the elimination, okay, followed by kind of addition, okay. Totally opposite kind of the opposite kind of the process, okay. And for this reaction, okay, so little bit broader kind of the substrate, okay. So only bromide, bromo, the bending or the chloro bending can you work, okay. So okay, so maybe write it down, okay. Two requirements, okay, for this reaction, okay. First one, okay, so you have kind of bromo or chloro, okay. Benzene as a starting material, okay. Chloro bending or the chloro bending or bromo bending as starting material, okay. And then second case, so this reaction requires strong base, okay. So this strong base sometimes also kind of the good nucleophile, okay. Strong base and good nucleophile, okay. So the attacking species has to be kind of strong base and also good nucleophile, okay. All right. And for the overall reaction, kind of so we'll start with kind of bromo or chloro kind of bending, okay. Right, and then you apply some kind of strong base and good nucleophile, okay. So this base kind of both strong base and good nucleophile. Replace kind of chloro or bromo, okay, and then that's you give kind of the final product, okay. So that's the base also work as kind of nucleophile, okay. All right, and for this reaction, okay, that's the mechanism kind of required, okay. Mechanism required, okay. So I may ask you guys kind of draw it kind of in future exam, okay. So for all three kind of the nucleophilic substitution reactions, okay. So the first two diazinuclein and also the addition elimination reaction not required, okay. But the last one, okay, elimination addition kind of required, okay. All right. So there's one specific kind of example showed on the screen, okay. So some kind of PPT, okay. Here I just show you guys kind of the very general kind of the mechanism, okay. What's going on, okay. All right. Right, so I use kind of chloro as example, okay. All right, so first step, okay, so base, okay, so yeah, same time kind of nucleophile come in, okay, so yeah. Pick up, yeah, this, yeah, also hydrogens, okay, next to chloro, okay. And then you push electron like here the 3 times, okay, very similar to kind of here the E2 elimination, okay. Yeah, 3 times, okay. You generate some kind of here we call it the benzene, okay. Right. You see kind of here the original we have kind of double bond already, okay. So now we shift electron pairs here again, okay. So we get kind of triple bond, okay, triple bond, okay. So that's here why we call kind of here this species called kind of here benzene, okay. Benzene and alkyne, okay, benzene, okay. All right, and then next kind of here this guy, okay, strong base, strong nucleophile coming again, okay. All right, and then attack kind of open this CC triple bond, okay. All right, base is on, okay, and then negative charge here. We have also lone pairs here, okay. And then falling kind of here because the very beginning the base already pick up 1 hydrogen from bending, okay. So now it's give back, okay. Yeah, and then give kind of here the final product, okay. The final product I draw here. Yeah. So that's here the whole process, okay. So just keep in mind, okay, so we are generate kind of benzene intermediate, okay. So yeah, first step similar like here the E2 elimination, and then second step, okay, so it's pretty much kind of the we call it kind of yeah maybe somehow like addition reactions, okay, but yeah not exactly yeah, same as kind of electrophilic addition reactions, okay, this kind of yeah nucleophilic addition reactions, okay, and eventually kind of yeah pick up 1 proton from kind of yeah the nuclear base, okay, so yeah that's yeah yeah give kind of final product, okay. All right. Okay, so for this reaction, okay, so yeah, we generate kind of a benzene intermediate. Okay. Benzene, okay, although it has kind of a CC3 bond, okay, but here for the reality, okay, so yeah, these 2 carbon, okay, so yeah, it's kind of a CC3 bond, okay, still kind of sp2 hybridized carbon, okay, so yeah, remember, okay, so yeah, chemistry 1, okay, we learned kind of the alkyne, okay, so should be kind of sp, okay, hybridized, okay, but here this one, because still kind of the trigonal planar kind of structure, okay, should be kind of sp2, okay. And so you have 1 pair for kind of p orbital and kind of first double bond, okay, and second kind of the double bond, okay, so actually shared between these 2 sp2 orbitals, okay, 2 sp2 orbitals, okay. So that means kind of the stability of your benzene is kind of much weaker than regular kind of alkyne, okay, because the sp2 orbital, these 2 kind of the little bit far away from each other, so, okay, so not parallel to each other, you cannot get kind of the good overlap of the orbitals, okay. And then that means kind of benzene is not stable, okay, easily to attack by kind of the base or nucleophile, open the CC bond, okay, open CC3 bond, okay. And for this reaction, okay, so yeah, I will say kind of much more useful than the first 2 nucleophilic substitution reactions, okay, because this reaction you only need start kind of bromo bending and chloro bending, okay, so those are kind of pretty abundant, okay. And then second kind of this reaction kind of the starting material normally quite cheap, okay, so reaction conditions kind of okay, okay, so yeah, and then but the product is normally quite useful, okay, so you can generate kind of phenol or kind of aniline, okay. All right, and here, okay, so just show you guys, okay, why the people find this kind of benzene as intermediate, okay, so yeah. All right, so this reaction case here kind of that's starting material, okay. So if it's kind of directly do the substitution on the carbon with bromine attached, okay, so you should only get 1 product, okay. So that's probably this parallel substitute kind of product, okay. But for reality, we got kind of 1-to-1 the para substitute and also the meta substitute, okay. Reason for that case, so when you do kind of the elimination addition reactions, okay, so you generate kind of CC3 bond, okay, so yeah. So between the kind of the carbon with bromide attached and also kind of its neighboring hydrogen, neighboring carbon, okay, right? And then these 2 carbon has pretty much no difference, okay. So in this case, when nucleophile or base come in, okay, can attack any of these 2 carbons, okay, and then eventually get kind of the mixture, okay, get the mixture, okay. So why I said kind of this reaction kind of relatively useful because that's kind of the industrial way to prepare kind of aryl kind of amine, okay, aryl amine, okay. So yeah, the H2, okay, HR or R2, okay, and also industrial prepare kind of phenol, okay. So phenol we already learned one way kind of by the we call it the diazonium, okay. Remember, okay. So yeah, we just kind of the diazonium kind of intermediate, okay, and then react with some kind of the acid, okay. So yeah, under aqueous conditions, okay, we just kind of phenol, okay. But yeah, that's kind of too hassle, okay. So yeah. And then people just directly from kind of the benzo, chlorobenzene, okay, and then directly react with kind of sodium hydroxide, okay, high temperature, okay, so high pressure, okay, so immediately just kind of a lot of phenol, okay, so that's the much easier way, okay, so yeah. Okay, and then that's the one thing, okay, and give you guys one more example, okay. So that's we start with this we call kind of also the bromo toluene, okay, and then we apply some kind of strong base, also kind of good nucleophile, heat it up, okay. Right, so because we generate kind of benzene, okay, so between these two carbons, okay, so that means kind of we can have two products, okay. One also goes kind of OH goes also potassium, another kind of the OH goes kind of meta potassium, okay. All right. Okay, so that's about three nucleophilic substitution reaction, okay. And just keep in mind the last one kind of require you draw the kind of mechanism, okay. All right, okay. So now we'll study a bunch of reduction reaction and also the oxidation reactions, okay. All right, so we first will learn maybe 4 reduction reactions, okay. So yeah. All right. So the first one is kind of converted the nitrobenzene to aniline, okay. So yeah, so NH2 to kind of the NO2 to NH2, okay. First one, reduce. NO2, okay, so that's aromatic, okay, so can be benzene, okay, into kind of the NH2, okay. All right, so the reagent that we can use for this reaction, okay, actually kind of 3 kind of reagent can do this work, okay. The first one kind of we call kind of catalytic hydrogenation reactions, okay. So yeah, you kind of the nitrogen, okay, with kind of platinum, okay. Palladium kind of probably also work, okay. Palladium also work, okay. So all right, so that's first one. And then second one kind of you use iron with kind of the HCl, okay. Yeah. So yeah, the chlorohydrin, the hydrochloric acid, okay. So yeah, FeSCl, okay. And then third one, okay, so that's we use tin chloride, okay, with HCl, okay. Yeah. So either of these 3 conditions can do this conversion, okay. So convert kind of NO2 to kind of NH2, okay. And the example showed here, okay. So yeah, the first reaction use kind of the catalytic hydrogenation reaction conditions, okay, and then hydrogen PT, okay, and then convert kind of NH2 into kind of the NO2 in NH2, okay. The key thing you can see kind of there kind of ester, okay. The ester has no reaction to this kind of the catalytic reaction conditions, okay. So later we'll talk about kind of selective kind of the reduction, okay. So yeah, that's the one case, okay. And then second one is kind of we use iron and HCl, okay. So yeah, that's can reduce both nitro group into kind of the amine, okay. All right. So for this reaction, okay, so one thing you just keep in mind, okay. So yeah, that's probably the first reaction we learned how do we prepare kind of aniline nitro group okay, amine group on benzene okay, because yeah, so far yeah, the reaction we learned kind of yeah, just to prepare other kind of substitute group okay, that's the first one okay. And then second thing is kind of yeah, you can yeah write it down okay. This reaction convert kind of yeah meta director into also para director okay. All right. So nitro groups kind of yeah, the active group case also meta directors okay, but yeah, the amines kind of the yeah active group case so yeah, the also para directors okay. So yeah, somehow kind of quite interesting kind of yeah be using kind of CC design okay. All right, give you guys one example okay. All right. So for example, in the quiz exam, okay, I'll ask you guys kind of yeah, try to yeah make this kind of yeah we call the yeah meta bromo kind of aniline okay from kind of benzene. Okay, that's bromo okay, bromine Br okay. All right, so yeah, if you take first look, okay, so yeah, we use our kind of strategy, kind of yeah, yeah, for the beginning of this class, okay, so analyze kind of which one we put on first, okay, you find that either one is not work, okay, so if we put kind of NH2 on, okay, right, so NH2 kind of yeah, yeah, also para directors, okay, so even you protect it, okay, so still also para, okay, and if you put kind of yeah BR on, okay, so yeah, BR is also kind of also para directors, okay. So no way you can yeah put yeah these two kind of yeah first okay and then another one on also para positions okay. Right, so that's yeah we can use yeah yeah this yeah yeah convert NO2 to NH2 okay so strategy okay. Right, so for this reaction okay so the first step we can do kind of yeah do nitration reactions okay. Nitric acid and then sulfuric acid okay. We put here the nitro group down okay. All right, so that's how we already learned it. Okay, and then the nitro group can also para directors. Okay, so it's kind of a meta directors. Okay, so no problem. We can do kind of a bromination, put a bromide Br on kind of the meta positions. Okay, so that's iron bromide. Okay, all right, and then all right, okay. So that's give kind of meta substitute kind of a bromide. Okay. Okay, and then in that case, so we can use here. Okay, so reduce here the yeah NO2K into NH2K. So yeah, you can use kind of yeah iron with kind of yeah HCl. Okay, yeah, that's good. Right. So that's something yeah keep in mind. Okay, so in the end of this chapter, okay, I will talk about kind of more yeah this kind of yeah trick. Okay, so yeah, how do you kind of yeah yeah convert kind of yeah autopara to yeah meta or kind of yeah convert kind of yeah the meta to autopara directors. Okay, yeah. Right, so that's the first yeah the reduction reaction, and then another three reduction probably we will learn them kind of all together. Okay. Okay. Because yeah, they do the same reaction, actually kind of similar reactions. Okay, so the first one, okay, so that's we call kind of like Clemmensen reduction. Okay, right. And then second one called kind of yeah, Wolff-Kishner reduction. Okay, leave a little bit of space here. Okay. Wolff-Kishner reduction. Okay. And then last one we called kind of the catalytic hydrogenation reduction. Okay, yeah. Right. All right. So all three reactions actually kind of yeah do the same thing. Okay. So yeah, convert kind of yeah ketone. Okay. So yeah yeah aromatic substitute kind of ketone okay into kind of yeah 可能看到 ketone 看到是substitute 看到aromatic compound into 看到alkyl group substitute 看到aromatic compound. Okay, so pretty much what happened 看到this CO bond is gone. Okay, become CH2. Okay, so all three do the similar reaction. Okay. Yeah, all three do a similar reaction. Okay. Okay, so the key thing difference kind of there are reaction conditions. Okay. For the Clemmensen conditions. Okay, so that's you have kind of zinc mercury. Okay, so under acid conditions. Okay, so that's actually kind of should be called what's this called kind of zinc normigate kind of zinc normigate zinc. Okay, so under acid conditions. Okay, so that's a very special kind of reagent. Okay, so amalgamate kind of zinc. Okay. All right, and then on the acid condition you can totally remove here. Okay, and for the Wolff-Kishner reactions. Okay, so you find kind of we use the hydrogen. Okay. NH2, okay, under kind of the basic condition. Okay, so normally we use potassium hydroxide. Okay, both kind of actually kind of a pretty good base. Okay, right, and then we can cleave all kind of CO bond. Okay, and last one catalytic hydrogenation reaction. Okay, pretty much kind of just the hydrogen with palladium, platinum, okay, whatever. Okay, so all right, and then for this three reactions. Okay, so although they have kind of similar kind of reaction. Okay, similar the starting material and product. Okay, but the cases here. Okay, so the reaction condition. Okay, so for the Clemmensen conditions. Okay, so that's the under acid conditions. Okay, and then for the Wolff-Kishner reactions. Okay, that's actually kind of under basic conditions. Okay, and last one kind of pretty much you do it kind of neutral. Okay, so Okay, so in this case, the depends on what kind of the function group. Okay, already on the benzene ring. Okay, so you can choose the waste reaction conditions. Okay, for example, okay, so if you already have you already have kind of for example, kind of amine. Okay, on the benzene ring. Okay, and then you try to reduce this guy. Okay, into kind of this compound. Okay, all right, so amine is kind of relative kind of basic functional group. Okay, so in this case here you don't want to use kind of Clemmensen reduction conditions. Okay, because that's kind of acid. Okay, so if you use Clemmensen conditions. Okay, so acid base reaction will happen. Okay, so that's the scrub. Okay, so you kill the base, kill all the acid kind of probably won't get the reaction work. Okay. But you can use here the Wolff-Kishner reaction conditions. Okay, because that's kind of pretty much basic conditions. Okay, won't have any reaction with amine. Okay, so you have kind of NH2, and potassium hydroxide. Okay, similar thing. Okay, so if you have acid functional group. Okay, so for example, we have kind of the sulfonate kind of acid. Okay, on the benzene ring. Okay, and then we try to do some kind of the reduction reactions. For example, okay, so we do this guy. Okay. All right, so that's you will pick up kind of a Clemmensen reduction conditions. Okay, because both acid. Okay, acid has no reactions. Okay. Someone asked questions. Okay, what condition did you write for catalytic? Catalytic H2PD. Okay, H2 is kind of hydrogen. Okay, H2. Okay, and then PD is the palladium. Okay, palladium. Okay, palladium. Okay. Right. Some other questions. Neutral. Okay, neutral. Okay, so this one kind of pretty much just neutral. Okay, so no basic and also no acid. Okay, all right. Okay, so that's if we have kind of acid kind of starting material. Okay, and then we use Clemmensen conditions. Okay, zinc mercury with kind of the acid. Okay, right. So that has no reaction with kind of the sulfuric acid. Okay, and then that easy convert kind of just acid group. Okay. Okay, and then following kind of for some kind of interesting about these three reactions. Okay, for the Clemmensen and those the Wolff-Kishner. Okay, so these two. Okay, you can reduce any kind of ketone or aldehyde. Okay. Right, reduce ketone aldehyde to just kind of alkene. Okay, yeah. So these two. Okay. So what's that mean? Okay, so these two not only you can apply to kind of kind of the aromatic kind of ketone, you can regular ketone, you can also do it. Okay, so for example, I have kind of just a very easy example. Okay, right. So that's the ketone. Okay, and you apply these two conditions. Okay, for example, we apply kind of the Wolff-Kishner reaction conditions. Okay, yeah, that's it. Okay, so that's you can use this either of these two. Okay. But for the last one, okay, so the catalytic hydrogenation reactions, okay, so you cannot do this, okay, you cannot do this, okay. So you have to kind of make sure that the CO bond, okay, next to kind of directly bound to kind of the benzene, okay. Yeah. So directly bound to kind of aromatic compound, okay. So yeah, that means kind of it has to be kind of the aromatic kind of ketone, okay. So yeah, cannot be regular ketone, okay. So yeah, that's something you can keep in mind, okay. All right, and then after the that's totally full reduction reactions. Okay, so now we learn one kind of the oxidation reactions. Okay, called kind of the benzoic oxidation. Okay, so that's so for benzoic oxidation, actually kind of has no reaction on the kind of a benzene case. So actually happen kind of if you have some kind of acute chain attached to benzene case. So general reactions like something like this case, you have kind of acute chain attached to the benzene or other aromatic compound case. And then you apply some kind of oxidation reaction conditions case. You cleave off kind of oxidize kind of whole acute chain into kind of the carboxylic acid case, COH. Okay. And there are kind of two conditions can do these reactions. Okay. First one kind of you use the potassium permanganate K. And under some basic condition K, so yeah. So sodium hydroxide, potassium hydroxide K. So yeah, this one actually kind of two-step K. So step one K, so yeah, use kind of this, and then step two K, so a little bit acidified K, so work up K. So yeah, that's first one K. And second one kind of you can use the chromic acid K. H2CrO. Okay, so yeah, both can just kind of oxidize kind of the aromatic compound. Okay, so yeah, the acute chain okay, on kind of carboxylic acid. Okay, right. So for this reaction, okay, so yeah. Okay. So for this reaction, okay, just one thing keep in mind, okay, it's required the benzoic carbon, okay, so has at least one hydrogen attached. Okay, so what's benzoic carbon? Okay. So that means kind of the carbon directly attached kind of benzene K, directly attached benzene K. So yeah, doesn't matter kind of what's attachment on this carbon, doesn't matter, okay. But this one has at least one hydrogen on it, okay. So if there's no hydrogen on this carbon, okay, no these reactions, okay. So that's also here, okay. So that means here the benzoic oxidation reaction only happens kind of for primary, secondary, tertiary benzoic carbon, not for the quaternary. Okay. So quaternary, okay, you have 3R group, okay. So no hydrogen on this carbon, okay. So that means kind of no kind of reactions, okay. So no reactions, okay. As long as there's only one hydrogen on this, okay, no problem, you can do this, okay. So yeah. All right, and then for these reactions, okay, so kind of pretty kind of strong and also very kind of high efficient, okay. So yeah, even you have kind of multiple alkyl group, okay, you quickly follow all kind of alkyl group and convert all them kind of into the Carboxylic acid, okay. So one example showed here, okay. So yeah, we have kind of the dimethylbenzene, okay. All right, so yeah, two methyl group, okay. So yeah, both they become kind of Carboxylic acid, okay. So both Carboxylic acid, okay. Both ethyl group has kind of the hydrogen attached, okay. Right, and I'll give you another example, okay. All right, so we have this starting material, okay, try to do the benzoic kind of oxidation reactions, okay. All right, okay, and then if you take a look, you find okay, so this carbon has kind of two hydrogen, no problem, you can get kind of benzoic oxidation, okay. But this carbon, okay, that's quaternary carbon, okay, has no hydrogen attached, okay. So in this case, okay, after reaction, okay. Yeah, that's the product, okay. Okay, so that's something keep in mind, okay. And then I remember, okay, so give you one more example, okay. So last year actually probably from last year quiz of exam, okay. All right. All right. So we try to apply kind of the benzoic oxidation reaction conditions, okay, to this compound, okay. All right, so yeah, a lot of students get confused. Okay, so what's going on? Okay, so yeah, kind of the benzene ring next kind of six membrane. Okay, so yeah, actually kind of don't care. Okay, don't care. Okay, so yeah, oh yeah, no matter how long or how branch of this kind of alkyl group. Okay, as long as there's one hydrogen on the kind of benzoic carbon. Okay, so this is benzoic carbon. This one has one hydrogen. This one has two hydrogen. Okay, you cleave all the off. Okay, cleave all the off. Okay. And eventually the final product look like this, okay. Yeah, that's it, okay. So that's here the why the benzoic oxidation reaction kind of pretty high efficient, okay. So even you have kind of 100 molecule kind of branch here, okay, so all gone, okay, so become COH, okay. Otherwise you have kind of the hydrogen on the kind of benzoic carbon, okay. All right, okay, so that's the pretty much we done the kind of the reaction for these chapters, okay. Here's a little bit summary of the reaction, okay, we learned in these chapters, okay. So first, we learned kind of 5 EAS reactions, okay. So sulfonation, okay, and then the first one nitration, okay, second kind of sulfonation, and then followed by kind of the chlorination or bromination, and then free crack kind of the acylation, free crack acylation, okay. So only sulfonation is kind of the reversible reaction, okay. And then we learned some kind of nucleophilic substitution reactions, okay. Nucleophilic substitution reactions, okay, so the first one kind of diazonium, okay, so has to be started with kind of aniline, okay. And then two-step reaction, first step convert kind of the diazonium intermediate, okay. And then you can do all kinds of the substitution reactions, okay, put a different kind of nucleophile on it, okay. And then we also learned kind of another two nucleophilic substitution reaction that we just learned today. One is kind of this one kind of the elimination and followed by kind of addition. Okay, so that's you have to start with kind of chlorobenzene or bromobenzene. Okay, we use strong base. Okay, and also strong nucleophile. Okay, same time. Okay, so do substitution reactions. Okay, use benzene as kind of intermediate. Okay. Also, you can do kind of the addition elimination reaction. Okay, so this one has kind of more elimination. Okay, so you have to make sure that kind of leaving group electron withdrawal. Okay, and also parity positions of the chloro, bromo, or kind of aldo, frodo, okay, whatever. Okay, and then you apply some kind of nucleophile. This nucleophile don't need be strong kind of base. Okay, as long as kind of good nucleophile can go do these reactions. Okay. And then we learned a bunch of the reduction oxidation reactions. Okay, so you can reduce the nitrobenzene into kind of aniline. Okay, so we use kind of 3 conditions we just learned. Okay, also you can reduce this kind of benzene ketone, ketone benzene into kind of just alkyl chain. So 3 conditions. Okay, so Wolff-Kishner or kind of kind of Clemmensen conditions or kind of catalytic hydrogenation reaction conditions. Okay, so a little bit careful about kind of acid condition or kind of basic conditions. Okay, and then next kind of just the benzoic oxidation reactions. Okay, so it's kind of cleave off kind of the alkyl group okay, into kind of COH. Okay, and so let me see. Okay, so I remember. Yeah, here. Okay. And so all these reaction actually kind of also I put on kind of into a PDF file upload online. Okay, so you can download the study. Okay, so for example, the first kind of 5 ES reaction, what's the electron file, okay, and then what's product, okay, and what's reagent, okay, and then what's kind of comments, okay, so some kind of important thing you have to take in consideration. For example, the Friedel-Crafts calculations and 3 drawback, okay, so and then there's kind of a nucleophilic substitution reaction, 3 nucleophilic substitution reaction, and then kind of the reduction reaction and also the oxidation reactions. Okay, so you can use it kind of for your the homework or kind of whatever. Okay, but you cannot use it this chart for the exam quiz. Okay, so you have to memorize all these reactions. Okay. So the tricky thing about this reaction, the chapter of this reactions kind of some the synthesis design. Okay, so because there are a lot of small things you have to keep in mind. Okay, so that's each time when I reach this chapter, kind of something that kind of that's kind of a little bit hassle. Okay, so when we talk about kind of synthesis design. Okay, so so that's here I try to a little bit summary kind of the synthesis design kind of the situation. Okay, you have to a little bit take into consideration. Okay, so when you try to kind of complete some kind of synthesis design questions. Okay. And the first one kind of the Dirac effect. Okay, so you have to attach kind of the group in the right order. Okay, so last year already said kind of if you try to think kind of para disactyl benzene case, so try to kind of put auto para director on kind of first, okay, and then put second one. Okay, if you want to make kind of meta substitute kind of the disactyl kind of benzene, try to put kind of meta director on the benzene and then do kind of the substitution reactions. Okay. All right, and then last one. Okay, so give you guys one example. Okay. All right. So we try to make here this here the 2 compound from benzene. Okay, so you one kind of nitro group, one kind of bromine. Okay, all right. So you see kind of one kind of para disactyl, one kind of meta disactyl. Okay, so you have to think about which one do you put on first. Okay, all right. So for the first one, because kind of meta disactyl. Okay, so that means kind of the first step you need to kind of nitration, put the nitro group on. Okay, because the nitro group is kind of meta director. Okay, and then second step, okay, you do kind of bromination. Okay, so put bromine on. Okay, all right, and then second one, okay, so this time kind of you have kind of the para disactyl situation. Okay, so that means kind of you need to put bromine on first. Okay, because the bromide is the para directors. Okay, para also directors. Okay, and then second kind of you do the nitration. Okay. Okay, so nitration reaction product, maybe you can get some kind of also substitute product. Okay, so that's it's okay. So we can separate it. Okay, also for this kind of reaction. Okay, so normally speaking, I prefer go to the para position. Para position has kind of last bulky kind of last there hindrance. Okay, so that's the first thing you have to think about it. Okay, and then second thing kind of if you want to since it's kind of the primary the alkyl substitute kind of benzene case, so then you can apply kind of IFC oscillation combined with reduction reactions. Okay, so what's that mean? Okay. Right, so we always know that kind of for the IFC kind of accumulation reactions, okay, so can have kind of rearrangement, okay. So in this case, yeah, if you want to, make kind of a primary alkyl group substitute kind of bending, okay, from bending, okay. So you cannot directly do the IFC accumulation, okay. So you remember in the class yesterday, okay. So if you directly do the IFC accumulation, okay. So yeah, if you want to apply this reagent. Right, so won't give you kind of desired product, there kind of rearrangement will happen, okay, give you kind of the isopropyl substitute group, okay. So in this case, yeah, if you really want to do this reaction, actually kind of you do indirect way, okay. We start with bending, okay, and then we can do kind of the IFC oscillation first, okay. Right, so that's the propionyl kind of chloride, okay. Propionyl kind of the propionyl kind of chloride, propionyl chloride, okay. So yeah, and then ArCl3, okay. So that's we IFC kind of oscillation reaction has no rearrangement, okay. So yeah, right, and then you can do the reduction reactions, okay. So any of these reduction conditions, okay. You can do kind of Clemmensen kind of the reduction, okay, or kind of Wolff-Kishner reduction, or kind of catalytic hydrogenation reduction, okay. So here I use catalytic hydrogenation reduction conditions, okay. Right. So that's you get kind of primary substitute kind of the primary alkyl group substitute kind of the bending, okay. So that's the something you need to take into consideration, okay. There's some other synthetic design kind of topic, okay. So yeah, we stop here, okay. So we'll talk about continue the synthetic design kind of on Monday class, okay, in the Monday class, okay. Yeah, all right, okay. So do you guys have any questions? Yeah, you can type in the chat window, okay. So pretty much we already done the chapter 17, okay. So just some kind of synthetic design problems, okay. And so in this case, yeah, over the weekend, okay, I'll post some kind of homework online, okay. So you guys can start work on it, okay, both on the smart work homework and also the actual credit homework, okay.